Hello friends, welcome to the video lecture series on basic electronics. I am Dr. Dafda and today we will study digital electronics and logic gates. So let us start as usual, starting with the name because everything is there in the name. What is digital electronics? Digital electronics means electronics that deals with digital signals or fixed signals or discrete signals. See, transistor as an amplifier, transistor as an oscillator circuits which you have learned in previous video lectures are analog circuits because it is dealing with signal that is continuously varying with respect to time, whereas digital electronics is one which is dealing with digital signals or fixed signal with respect to time, particularly a pulse waveform or you can say 0101 waveform, right? And what are logic gates? As the name suggests, gate is a device that allows something or restricts something to pass through it, and logic means intelligence, right? That means logic gates are the devices which are controlling the flow of information through it logically or through the intelligence that is provided to it. So this is a digital signal which you can see here. Okay, this is time axis and this is voltage amplitude. So you can see here the digital signal is having only two levels, a 0 level and level 1. Again 0 level, level 1. Whereas this one is your analog signal. This is time axis and this is voltage amplitude axis, and you can see here that this signal is varying continuously with respect to time. Okay, so such a signal is known as an analog signal, right? Whereas this signal which is fixed with respect to time is known as digital signal. Now if you take any particular points on these signals, right, as I have shown here, say these points are T1, T2, T3, T4 and T5. So let us compare both the signals. So if you compare both the analog signal and the digital signal, you can see for T1 the analog signal is having some value over here, right? For T2 it is having some other value, for T3 again it is having some other value, for T4 it is again having some other negative value, even for T5 it is having some other negative value, right? So you can see here that the values of the voltage amplitude is varying continuously with respect to the signal or with respect to time axis, right? Whereas see the digital signal, for T1 the value is 0, for T2 again value is 0, for T3 the value is 1, you can see here the value is 1, for T4 again the value is 1, for T5 again the value is 0. That means analog signal has got infinite number of values with respect to time, whereas the digital signal is having only two values, a 0 value and a 1 value. That means a 0 level and a 1 level, right? The value of this digital signal for 1 level ranges from 4.5 volts to 5 volts, whereas for 0 level it ranges from 0 volts to 0.5 volts. That means anything in between 0 to 0.5 volt will be considered as level 0, and anything in between 4.5 volt to 5 volt will be considered as level 1, right? So the transistor as an amplifier circuit, operational amplifier circuit, etc. are analog circuits, right? Whereas logical gates, integrated circuits, etc. are examples of digital electronics, right? Now you may be having question in your mind that what are the differences between this analog electronics and digital electronics. See, before giving you the differences between the analog electronics and digital electronics, let me give you three examples of digitization or advantages of digitization, right? First example is, we were using CRT TVs until recent few years ago. So these analog TVs or CRT TVs were very big, very huge and very heavy, and also power consumption was very large, but still the picture quality was not that good as we are obtaining with today's digital HD TVs or 4K TVs, right? Because today's TVs are very slim, they are very consuming very less power, and still the picture quality is brilliant and the resolution is excellent. So these today's televisions, flat TVs or LED TVs are digital TVs. Second example, before few decades, 2-3 decades, we were using audio cassettes which was storing the songs on an audio tape in an analog form, right? Whereas today we are using CDs or pen drives or hard disk which is saving our audio signal in the form of zeros and ones. So you have seen or you know the advantages of this digital CDs, right? The sound is crisp, clear as compared to the cassettes that we were using, and on the same price or even at a lower price as compared to those audio cassettes. The CDs or pen drives can store hundreds of songs, whereas those audio cassettes hardly could save 10 songs, and still the quality deteriorated with time. Whereas for the digital CDs or digital drives, you can replicate the data as many times as you want, and still the quality is far better as compared to the analog CDs. Third example is, we are still using the landline telephones at many places, right? So you know these landline telephones are analog telephones. The signals which is received and transmitted is in analog form. So you know what are the problems of that particular telephone. Okay, during monsoon season you cannot hear the sound properly, there is lot of noise and disturbance, and you know the size of that telephone, very heavy and bulky, right? You just cannot carry anywhere. Whereas today's digital smartphones or mobile phones which are digital are having a very good or great sound quality. You can even do video calls, you can use internet on that phones, and of course you can use that as a normal phone also. So these three examples shows how digitization has revolutionized our modern world, right? So now let us see the differences between digital electronics and analog electronics. For analog electronics or analog signal, if the noise gets added to the signal, it is very difficult to remove it. Whereas digital signal is very much noise proof. Why? Because there are only two levels. Any intermediate levels or any irregularities can easily be removed from this digital signal. Second thing, it is very easy to store and transmit the digital signal because the storage and transmission is only in the forms of zeros and ones, right? Whereas it is very difficult to store, transmit the analog signal. Third, to make the replica of a digital signal is very easy. You can store it in as many number of times, or you can replicate it as many number of times as you want. Whereas for analog signal that is not possible. And other important advantage is that these digital signals are very fast, very fast, and analog signals cannot be that fast. Okay, and those are the advantages of this digital signal or digital electronics as compared to the analog electronics, right? And therefore today everything is digitized, or there is digitization everywhere, right? But remember, the real life signals are analog signals or time varying signals. For example, the speech or audio signal which we speak is something like this, a continuously time varying signal, right? Similarly, the temperature is also continuously varying with respect to time, pressure is also continuously varying with respect to time, air quality is also continuously varying with respect to time. So meaning is to say that the real life signal or real world signal are analog signals, right? Then you may be having question in your mind that why we are converting these analog signals to digital signal. Due to the advantages which I just mentioned, due to all the advantages of removal of noise, speed of transmission, ease of storage, due to all these advantages, we always convert the analog signal to digital signal at the transmitting side, and at the receiving side again we convert back the digital signal into analog signal. Okay, and the devices which are converting analog to digital are known as analog to digital converter, and digital to analog are known as digital to analog converter or DAC, right? Now you all know that a computer is an electronic brain, but I will modify the statement over here. I will say that the computer is a digital electronic brain. Why? Because computer is storing all the data in forms of zeros and ones only. Computer doesn't know any intermediate values or other values. Computer doesn't know ABC. Computer only knows zeros and ones. For example, say this particular level is my A, this particular level is my B, and this particular level is my C. So if for this particular level, for A, right, computer will not be storing A, but rather computer will be storing it in digital form. Say A means 0, 0, 1, right? Say for example, right, A is 0, 0, 1, B is equal to say 0, 1, 0, and C, say for example, is 0, 1, 1. So say for example, on my computer is stored 0, 1, 1, 0, 0, 1 and 0, 1, 0. Then what does it mean? See, 0, 1, 1 is C, right? 0, 0, 1 is A and 0, 1, 0 is B. That means I have written the word or stored the word CAB cab on my computer. Okay, but I cannot write CAB, okay, because computer does not understand CAB. Computer only understand this 011, 001 and 010. So if you type CAB, this will be stored on the computer, for example, right? So that means my computer will know that CAB or cab is stored inside it, right? So this is how the analog signal is stored into digital form, and this is how even the analog signals are converted into digital form by storing in forms of bits, right? Now digital signals are normally in binary form. So binary has got only two digits, 0 and 1. Remember, binary has got only two digits, 0 and 1. This 0 and 1 are known as bits, right? Now there are few laws of Boolean algebra which we may not be studying completely in detail over here, but you can remember very simple laws, that if A is equal to 0, then A bar is equal to 1. That means bar of anything is invert of that particular thing, right? So if A is 0, A bar is equal to 1. There are other simple rules such as 0 plus 0 will give 0, obviously. 0 plus 1 will give 1, right? Because it is 1, right? 1 plus 0 will also give 1. That is also quite obvious. But 1 plus 1 will not be equal to 2. 1 plus 1 will be equal to only 1. That means high level plus high level will be equal to high level, right? So this particular operations, the addition operations, is known as ORing or OR gate, right? We will just see what are gates, right? Similarly, 0 into 0 will give you 0, 0 into 1 will give you 0, and 1 into 0 will give you 0, but 1 into 1 will obviously give you 1, right? So this particular operation of multiplication is known as ANDing. And so this is how addition and multiplication are done inside the computer, and you can do lots of such arithmetic and logical operations inside a computer using the gates, right? So now let us come to gates. What are gates? So as we have just seen in the introduction, gate means one that allows something to pass or restricts something for passing. So a logical gate is a digital circuit that follows certain logical relationship between the input and output voltages, right? So there are certain logical relationships which are mentioned by truth table. Why it is known as truth table? As the name suggests, it is the true, or it is the rule or law for that particular circuit. Therefore it is known as truth table. That circuit will only follow the truth and nothing else, right? So the logical gates control the flow of information logically, right, or intelligently. So that is intelligence, or you can say how intelligence is stored inside the computer, right? You all are listening to the word artificial intelligence today, right? So that intelligence is also related to such intelligence, right? And these logical gates are the fundamental building blocks of digital ICs. Remember, the logical gates are the very smallest building block of any digital integrated circuit or any microprocessor or any computer, right? Microprocessors, microcontrollers, computers may have millions of such logic gates, right? And these logic gates are used everywhere, not only in computers. They are used in calculators, they are used in digital watches, they are used in industrial systems, they are used in televisions, they are used in music systems, okay? They are even used in your washing machines. Everywhere there is electronics or digital electronics, such logic gates are used, right? So what is the example of this logic gate, right? See, such logic gate is also present in your home normally, right? For example, a light switch in your house, okay, is also a logic gate. Why? Because it will switch on the light depending on the switch position. If you switch it on, the light will glow. If you switch it off, the light will go off, right? So that is also a type of logic gate, but here we are talking about logical gate that is electronic in nature, right? So this logical gate will be allowing or controlling the flow of information logically. See, there are many types of logic gates, but you will be studying 5 types over here: a NOT gate, OR gate, AND gate, NAND gate, and NOR gate. Of course, there are other gates also like XOR gate, XNOR gate, etc., right? But we'll be studying only these 5 gates as per your syllabus, right? So let us start with a NOT gate. So this is the logical symbol for a NOT gate. The first one is NOT gate. This is the logical symbol for it, right? There is one input and one output, right? And the logical symbol is almost same as a diode, but remember, In diode, there was a line over here and there was not a circle. For a NOT gate, there is a circle over here. So this is first thing which you should remember, the logical symbol for a NOT gate. Second thing, you should remember the truth table, because this intelligence of this logic gate is only this truth table, right? As it is binary system, 2 raised to 1, right? Because your input is only 1. So number of possible output will be 2 raised to 1, which is equal to 2. So if A is 0, output Y is 1. If A is 0, output Y is 1. If A is 1, output Y is 0. So this is the truth table for this particular logic gate, and this logic gate will only follow this truth table, right? So there are two outputs you can say here. Now what is the meaning of this NOT gate? This NOT gate is nothing but an inverter or a unfollower of the input, you can say like this, right? You can take the example like this, that this NOT gate is one of your younger naughty brother or sister, right, which will not follow your instruction, right? If you say, if the TV is switch on, and if you say switch off the TV, they will keep the TV on. You say switch off, they will keep it on. You say keep it on, they will switch it off, right? So they are not following your instructions, right? They are inverting whatever instruction you are giving to it, and therefore this is known as an inverter, right? That means if it is 0, it is 1. If it is 1 at the input, the output is 0. So you can say output is invert of the input. So input is A, so output is invert of that. That means output Y is equal to A bar. Now let us come this side and try to understand it. Okay, say this is a gate. It is a NOT gate. That means it will not follow your instruction. Okay, it will invert whatever you give at the input, right? It is your naughty brother or sister, younger brother or sister, that will not follow your instruction, right? So if the input is present, the gate is closed and output is 0. But if the input is not present, the gate will be open and output will be 1, right? See, input is 0, output is 1, input is 1, output is 0, right? Input is 1, gate is closed. Input is 1, gate is closed. But input is 0, gate is open and output is 1. Getting it? So Y is equal to A bar. Getting it? Okay. So how to make this logical gate or NOT gate inside the computer? It is very simple, right? You have already used, or you already know how to use transistor as a switch, or you even know how to use a diode as a switch, right? So you can connect a diode over here, and that diode, when forward bias, will be on, and when reverse bias will be off, right? So for NOT gate, this type of arrangement will be there, right? You can see here I have applied a voltage over here to a lamp, right? And I have connected a switch over here, right? So when this switch is open, at that time what will happen, that the current will flow through this lamp and the lamp will glow, right? Because open switch will provide infinite resistance and no current will be flowing, right? And the current will be flowing through the lamp. That means when A is 0 or open, Y is 1. When A is 0, Y is equal to 1. Now say I close this switch, then what will happen? The closed switch will provide a low resistance path for this current that is flowing through it, right? And hence what will happen? All the current will flow through this path and no current will flow through this lamp, right? And the lamp will be off, will not be glowing. That means when the switch is closed or 1, the output Y is equal to 0, right? So this is how a NOT gate is, a very simplest gate. Let's go ahead and see the second gate. The second gate is a OR gate. So this is the symbol of a OR gate, right? There is a curve like this and there is a curved arrow like this, right? So as there are two inputs, right? It is 2 raised to 2. That means there will be 4 different combinations of inputs. There are 2 inputs A and B and 1 output Y. As the name suggests, it is a OR gate, right? So let us take one example. For example, there is no vegetable left in your fridge and your mother gives you 10 rupees and says you go in the market and buy a cabbage or a cauliflower, whichever is available, right? So if you bring cabbage, it is okay, that is valid. If you bring cauliflower, that is also valid. But you went to the market and you saw that both cabbages and cauliflowers are present and both are very cheap, right? Just 5 rupees per piece, right? So you decided to take both of them. and you bring both of them to the home and give it to your mother, so your mother will says yes, it is okay. If you do not bring cabbage or cauliflower, it is not valid, it is 0. If you do not bring cabbage and you bring cauliflower, right, it is valid, your mother will accept it. If you bring cabbage and do not bring cauliflower, again your mother will accept it. But if you bring both of them, again your mother is going to accept it. In fact, she will be more happy, right? So this is known as OR gate. Either cabbage or cauliflower or both of them, but none of them will not do. Getting it? Right? So see this particular image. Say A and B is 0, 0, gate is closed, output is 0. A and B is 0, 0, gate is closed and output is 0. See again. A, B 0, 0, output 0. 0, 1, output 1. 1, 0, output 1. And 1, 1, again output is 1. Right? See again. The OR gate will be open for 3 different conditions. 0, 1, 1, 0 and 1, 1. Right? But it will be closed when both are 0, right? See, when both A and B are 0, the gate is closed and no output is there. If B is present, output is there. If A is present, output is there. And if both are present, output is there, right? That means 0, 0 will give you 0, 0, 1 will be 1, 1, 0 again will give you 1, and 1, 1 again will give you 1. So this is the truth table for this OR gate, and it will follow this truth table. Okay, so it is given by y is equal to OR of A, B. Or you can say y is equal to a plus b, right? So whenever you are ORing, that means you are adding, right? Y is equal to a plus b. 0 plus 0 will give you 0. 0 plus 1 will give you 1. 1 plus 0 will give you 1. And again 1 plus 1 will give you 1, right? So that means OR means addition. Now let us come to the circuit of the OR gate, right? What will happen inside the OR gate, right? So for OR gate, the output will be available if A switch is on, the lamp will glow. If B is on, the lamp will glow. And if both A and B are on, again the lamp will glow. But if both are open, the lamp will not glow. That means if both are 0, 0, output is 0. If one is closed, say B is closed, then the current will flow through B and the lamp will glow. If B is not closed and A is closed, then again the current will flow through and the lamp will glow. And if both are closed, then also the current will flow through it and the lamp will glow. So inside the computer, such will be the circuit for a OR gate, right? And of course, these switches can be replaced by the diode or a transistor. Getting it, right? So that is OR gate. Okay, let us go to the third gate, that is AND gate. So this is the symbol of a AND gate. There is a straight line and there is a curve, okay, or semicircle like this. So there are two inputs A and B and output is Y, right? And truth table for this AND gate is like this. 0, 0 means 0, 0, 1 means 0, 1, 0 means again 0, and 1, 1 means again 1, right? So AND gate, as the name suggests, means it must fulfill or satisfy both the conditions. Let us say, for example, you want to cast your vote in the elections, right? You are not of 18 years of age, so you cannot cast, and you do not have any valid identity proof, so you cannot cast, right? Say you are not of 18 years of age and you have a valid identity proof, again you cannot cast your vote, right? Say you are 18 years old but you do not have valid identity proof such as Aadhaar card or election card or voter card, again you cannot cast your vote. But if you are 18 years of age and you have a valid identity proof such as Aadhaar card or voter's ID card, then you can cast the vote. Getting it, right? So that is one example for this AND gate. That means both conditions should be followed. Okay, you must be of 18 years of age and you must have a valid identity proof. That means AND word comes in the statement, right? Then only your statement will be fulfilled. For the OR gate, the statement coming was OR. You bring this cauliflower or the cabbage, right? Here the statement coming is you must be of 18 years of age and you must have a valid identity proof. Then you can cast, and you must have, right? Then you can cast. So that is the truth table for this AND gate, right? See over here. If both are 0, A and B are 0, output is 0 and the gate is closed. 0, let us see here. 0, 0, gate is closed, output is 0. 0, 1, gate is closed, output is 0. 1, 0, gate is closed, output is 0. And 1, 1, gate is open and output is 1. So that means it is y is equal to AND of AB, that is y is equal to A into B. Getting it? So how the circuit of this AND gate will be? Say there will be two switches that are in series with each other, right? So for the lamp to glow, A must be switched on and B also must be switched on. Say if A is not switched on and B is switched on, lamp will glow? No. If both are open, lamp will glow? No. If B is closed, lamp will glow? No. If A is closed, lamp will glow? No. If both are closed, lamp will glow? Yes. That means A and B must be closed, lamp will glow. Getting it? So that is AND gate. So AND gate is nothing but multiplication, right? Let us go ahead and see the next gate. Next gate is NAND gate, right? So as the name suggests, it is not AND gate. That means AND gate plus NOT gate. NAND gate is same as AND gate, which we have just seen. This is AND gate, right? Plus of NOT gate, the very first gate that we have seen. That means inverter. Getting it, right? So if you invert the outputs of AND gate, you will obtain NAND gate, right? So this is the logical symbol for NAND gate, same as AND gate, just a circle will come over here that will suggest that it is inverting the output of AND. Again, it has got two inputs A and B and one output Y. So this is the truth table of NAND gate, right? If both are 0, output is 1. If any one is 0, output is 1. If both are 1, then the output is 0. It is just inverting the AND gate, right? You remember like this, or see over here. Say these are your two inputs 0 0 0 1 1 0 and 1 1, right? AND output will give you 0 0 will be 0, this will be 0, this will be 0 and this will be 1, right? But NAND is bar of A dot B, right? NAND is equal to A dot B and invert that, right? That means A dot B is 0 and you have to invert this 0, that means output will be 1. Here again A dot B or A into B, 0 into 1 will be 0 and invert of 0 will be 1. 1 into 0 will be equal to 0 and invert of 0 will be equal to 1. And 1 into 1 will be equal to 1 and invert of that will be equal to 0. So that is NAND gate, right? So remember, this NAND gate is very important because this NAND gate and the NOR gate, which we are going to study next, are known as universal gates. Why? Because you can make all other gates using this NAND gate and NOR gate, right? So next, fifth one is your NOR gate, right? So NOR gate means NOT plus OR gate, right? But NOT comes after the OR, right? NOR is equal to OR gate, and after the OR gate you have to add a NOT gate. That means you have to invert the OR gate, right? The symbol is similar to OR gate. Okay, there is a curved arrow which you can see, okay, and at the end of the arrow you have to show a circle or a bubble. That means it will be inverting the inputs that will be obtained from OR gate, right? So this is a logical symbol for the NOR gate, right? And the truth table will be like this. See, for OR gate, when both were 0, it was output was 0. It is NOR, that means here output is 1. For OR gate, any one is 1, then output is 1, right? Again, any one is 1, output is 1, and both are 1, output is 1 for the OR gate. But here for the all the three ones, there will be zeros, right? You can see here from the truth table, right? For OR gate, A plus B is equal to 0, right? 0 plus 0 is equal to 0. That means inverting this will give you 1. 0 plus 1 is 1. Inverting 1 will give you 0. 1 plus 0 is 1. Inverting 1 will give you 0. And 1 plus 1 is 1. Inverting will give you 0. That means NOR gate is invert of A plus B, right? So that is NOR gate. Getting it, right? Now see, along with carrying out the mathematical and inverter operations, which we have just seen for different gates, right? These gates can also be used for modifying the pulse waveforms. Okay, how? Let us see. This is, say, signal A, right? This is T1, T2, T3, T4, T5 and T6, different time intervals, right? This is signal A and this is signal B, right? And so in between T1 to T2 A is 1, again between T2 to T3 A is 1, but in between T3 to T4 A is 0. In between T4 to T5 again A is 0, and in between T5 to T6 again it is 1, right? But B is 0 from T1 to T2, it is 1 in between T2 to T3, it is again 1 in between T3 to T4, it is 0 in between T4 to T5, and again 0 in between T5 to T6, right? So now let us draw different waveforms for different gates. Let us start with the OR gate. OR means addition, right? So I will write over here, right, that OR means to add, AND means to multiply, okay, and NAND will be invert of this AND gate and NOR will be invert of this OR gate. So let us start with the OR gate, right? See, in between T1 to T2, A is 1 and B is 0, and OR means addition, 1 plus 0. Okay, so what is 1 plus 0? 1 plus 0 is 1, so 1 level. What is 1 plus 1? 1 plus 1 is again 1, so 1 level. What is 0 plus 1? 0 plus 1 is again 1, so 1 level. What is 0 plus 0? 0 plus 0 is 0, so 0 level. And again, what is 1 plus 0? 1 plus 0 is again 1, so 1 level, right? Now AND gate, 1 into 0 is 0, so there will be 0 level. 1 into 1 will be equal to 1, so there is 1 level. Again 0 into 1 will be equal to 0, so 0 level. Again 0 into 0 will be equal to 0, so again 0 level. Again 1 into 0 will be equal to 0, so again 0 level, right? And what will be the NAND gate? NAND will be invert of this AND gate, right? So wherever it is 0 over here, for NAND gate it will be 1. Here it is 0, so for NAND gate it will be 1. Here it is 1, for NAND gate it will be equal to 0. Here it is equal to 0, for NAND gate it will be continuously be equal to 1 level, right? Similarly, for NOR gate it will be invert of OR gate. So for OR gate in between T1 to T2 it is 1. So for NOR gate it will be equal to 0, right? Again here it is 1 up to this level, up to T4. So up to T4 it will be 0. From T4 to T5 OR is 0. So NOR will be equal to 1, the invert of that. And in between T5 to T6 it is 1 level. So NOR will be equal to 0 level. Getting it, right? So this is how you draw different waveforms for different waves, right? Okay, you can even solve this by different truth tables, right? You have to write the truth table, or you can even remember the truth table and then you can solve, right? For example, for OR gate, 1 or 0 is 1, 1 or 1 is again 1, 0 or 1 is again 1, but 0 and 0 is not valid, so it is 0, and 1 in 0 is again 1. Similarly, AND means for AND both must be 1, and here only in between T2 to T3 both are 1, so it will be 1, right? So we will be solving few more examples on logic gates in the next video lecture, right? So that is all in this video lecture. I hope you have gained a good knowledge from this video lecture of digital electronics and logic gates. Thank you very much.